Hello. I cannot tell if... Hi, everybody. It's nice to see you all. I can't see... Oh, Zane. Oh, look, somebody. Nice to see you, Zane. I hope you guys are all having an okay start to the year, or more than okay, I should probably say. We're going to get started in a little bit. I just wanted to wait until some more people show up. Does anybody want to... Oh, hello, chemistry love. Ah, hi, Fatima. Nice to see you again. It's nice to hear from you all. It's nice to know I'm not just talking at my screen. Yes, Destiny. We have A-level biology as well. That was yesterday. You can come back next week. Hello, Ahmed. Nice to see you again, or see your typing again. Hello, Angelique. Hi, Alexi. It's nice to see you all. I think there might be a bit of a lag, but I think we're okay. Yes, I remember you. You've commented lots of times. Of course, I remember you. Let's give it another 30 seconds. I'm going to start sharing the presentation with you guys so that you can see that and not just my face. Dun, dun, dun. Okay. Hopefully you guys can see that in a second. I'm hoping. Yes. Haha, yes. Okay, there's definitely a little bit of a lag, but I'm hoping that will catch up soon. Let me try, I'm just going to really quickly try and fix that a little bit. Just bear with me. No, okay. All right, we're going to get started, people. So let's think about the rate equation. I'm really hoping that this is going to catch up. Right, so some of you have met me before because you were here on Tuesday. But just in case you don't know who I am, my name is Georgia. I'm the head of chemistry at SnapRevise. Just a little bit of background on me. I did a natural sciences sort of integrated BSc and masters, which means that I picked the degree that you do when you can't pick a science because you're indecisive. So I did mostly chemistry, but I also did a bit of neuroscience and other things too. And I've been teaching and tutoring chemistry for the last 6 years. So hopefully I can help you guys with your year 13 stuff. So what I want to do is sort of explain a little bit more about what these are. So if you don't know already, we have it's more of a recap than sort of all of the possible details that you need to know. So we're going to do key points, and I will mention the kinds of things that we won't be going over, so don't worry. We're also going to be doing some exam technique. So we're going to go through some exam questions and make sure you guys know how to handle those. And then we're going to have some time for you guys to ask me questions. As on Tuesday, this is free and it will also be free for the next few weeks. Oh, hello, Hiba. Hello, Anissa. It's lovely to see everybody. Yes, so these are going to be free for the next few weeks, but after that, they're going to be on the ultimate package of our new release, SnapRevise 2.0. There will be some free sessions happening a few times a month, but most of them will be on there. So I'll tell you more about that at the end. Let's talk about giveaways. So there's going to be, as on Tuesday, one person will be able to get a free account with us, which is really nice, a free subscription. So if you want to sort of enter that competition, you need to follow us on Insta and then share a picture of the web class on your story and tag us in it. And then, of course, it's only 24 hours, so it can disappear after that, and your friends will not have to see how dedicated you are to your learning for too long, or maybe they'll just respect that you want free stuff. And also, we're going to have another coupon code at the end that will end at midnight. So that's all sort of incentive to keep you guys here until the end, really. So I hope you stick around. The objectives for today. Ah, well done, Maisie. Yes, do you mean you got the free account? Because that's super useful. But yes, welcome back. I didn't see you yesterday, but I hope you had fun with my colleague. So yes, sorry, where was I? Objectives. So this class is going to be on the rate equation. So the first bit is going to be sort of like what that is, what the rate constant is, and how we figure out what order of reaction is. And then we're going to be looking at concentration time graphs and how you can figure out order of reaction from those. And then we're going to use concentration time graphs to figure out the rate constant for first order reactions only. So things I'm not going to cover really specific examples of experiments. There's some things with iodine that are really specific to exam boards that I'm not going to be doing. And initial rate experiments will be in the next web class. I know sometimes that comes under this heading as well, but we're not going to do that yet. So that will be next Thursday. So here are the spec points. If you were here sort of on Tuesday or yesterday, you'll know that I'm not going to read all of these out. You can just have a look. So if you're on AQA, this is what we're covering. As I said on Tuesday, you should really be revising and learning while keeping an eye on your spec points. So make sure that you're covering everything, use it as a to-do list. If there's anything that you feel like your teacher hasn't covered or that I haven't covered, you should really be taking responsibility for that yourself and making sure that you've got everything for your exam. Oh, yes, my lovely colleague has dropped you guys the link for the presentation. So if you want to be following along and writing in the things that I write in, that's super helpful for you. Just keep in mind that like when you sort of actively use your brain to like write things down or answer questions, you're going to remember things a lot better than if you were to just listen. Listening is good, but it's not half as good as doing stuff yourself. And then last of all, here's the OCR spec points. You can have like a quick glance through those, but I'm not going to hang around on this slide for that long. So yes, I hope you guys have had a good look because I'm about to move. Yes. Okay. So we're going to get started, and we're going to get started on things that we should already know. So the main bits for this web class is being able to convert between our different concentration measurements. So what we really want to think about is the fact that the standard one for most questions, the thing that you're going to be turning it into is what? Does anyone know? Does anyone know what it is? I'm looking out for the comments to see if, yeah, so we're in dm cubed, but it's something per dm cubed. And hello, Zane, thank you. Any ideas? Yes, Fatima, yeah. So that's the only bit you forgot, Zane. It's moles per dm cubed. And you can write that either like this, because if you remember your indice laws, putting a minus means over, or you can write it moles per dm cubed that way. Yeah. So does anyone remember how many centimeters cubed there are in 1 dm cubed? Anybody? So we've got 10,000, 10,000, 1,000, 1,000, 1,000. Yeah. Yes, you're right. You were right the second time, Maisie and Logan. And yeah, it's 1,000. So it's 1,000 for dm cubed to cm cubed, but it's a little bit different if we're sort of going over dm cubed. So if it's moles per dm cubed or moles per cm cubed, it's a bit different. Can somebody tell me what it is? How many? So I can also write it like this for you. So if it's 1 over dm cubed or 1 over cm cubed, how many centimeters cubed are in a dm cubed? 1 dm cubed? Anyone? Any ideas? Yeah. So this time it's 0.001. So that means that instead so for this one you would times by 1,000, but for this one you end up dividing by 1,000. So that's really important to keep in mind because you don't want to mess up your conversions by doing it the wrong way around. And last but not least, you see liters the least in exams, but it's good to have in mind anyway. Does anyone know how many liters 1 dm cubed is? Oh, thank you, Kaylee. So many people with the right answer. Thank you, everyone. 1. Yes. Yes, Alexi. Yes, Logan. Not quite Nadine or Nadine. It's 1. It's 1 liter. So that's sort of our basics. And it's nice because usually in year 13, there's a lot more basics that you really should have down pat. But the rate equation is quite a nice topic in that respect. So we're going to get started on the sort of new things. So the rate equation is sort of, it's based off of the way that we should be thinking about rate experimentally. So there's, I mean, like you could potentially think about rate, like how many times do particles collide in like a minute, but that would be really difficult to measure, right? So the way we think about rate in terms of experiments is usually the change in concentration of reactants or products over time. So this isn't the actual rate equation. This is just how we think about rate sort of logically for measuring in our experiments. Does anyone know how we write the actual rate equation? How we sort of convert changing concentration over time to the rate equation that chemists use? Anybody? I'm wondering if you've, yeah, so Maisie, you've given us a good start. There is a K involved. So rate equals constant K, and then there's something else that happens after that. So I've given you a bit of a clue there by saying change in, yeah, there's some square brackets. Can someone tell me what the square brackets mean? What is a square bracket? If not, I can help you out. Yeah, wicked, Maisie. Yes, TC, yes, Kushi, yes, Aisha. Yeah, so the square brackets mean concentration, and we're sort of giving our reactants randomly A and B. So it could be anything. It could be hydrochloric acid or it could be oxygen, but we're just saying placeholder letters, the concentration of A and the concentration of B. So rate equals K, which is a constant, and we'll talk more about that in a bit, times the concentration of reactant A times the concentration of reactant B. So that's sort of our basics. And this is the rate equation that you've got to remember for your exams. It will come up. It comes up almost every year. So it's very important for you guys to remember. So the rate equation, essentially the way we've written it, by writing rate equals K times A times B, we're suggesting that the relationship between rate and the reactions is directly proportional, i.e. like if we sort of increase the rate by 2, so if we increase A 2 times, so let's say we've got carbon dioxide and we've got like 3 moles per dm squared and we double that to 6 moles per dm squared, then the rate also times is by 2. That's direct proportionality. So it's sort of like the same thing. Like if we increase the concentration of A by 5, then the rate also times is by 5. That's sort of what this version of the rate equation is suggesting. Logan, you did not miss the thermodynamics web class. This is the first year 13 web class. You might, so different exam boards do year 13 in different orders, which just means that we had to pick the most common first topic, and the rate equation was the first topic. Hello, Squishy Ham. That is a very interesting YouTube name. That might be my favorite one for this session, Squishy Ham. Okay, so we do have some reactions that happen along those lines. So Squishy Ham, this is, it's gonna feel weird saying Squishy Ham. This is for both AQA, OCR, and EdXL. It's a merge of all of them. If I'm talking about something that isn't on one of the specs, then I mention it, but all of this stuff is pretty basic for all of the specs. So you are included in that. This is OCR. This might have come a little bit later on in the year for you, but this is the rate equation you definitely need to know. Cool, so back to it. So this rate equation is suggesting a direct proportionality, and that's called first order. That's a first order reaction when if you times the reactant by something, the rate gets timed by the same thing. So we use this proportionality sign and we say that the rate is proportional to A. So it's kind of like, it's almost like the infinity sign, but like not joined up. So I'm just going to put something like, if the concentration of A times is by 5, then the rate also times is by 5. If something is second order, it means that the rate is proportional to A something. Does anyone know what it means it's proportional to? A to the power of something. Any guesses? All guesses are good. Yeah. Yes, Shell. Yep. Yep, Vivian. Yep, Squishy Ham. It's A squared. So second order means that if, let's say, A ends up being times by 3, then the rate ends up being times by 3 squared. So that's a second order reaction. Third order. Can somebody tell me what they think third order might be? And I'll be super impressed. Yeah, yeah, cubed. Wicked. So the rate is proportional to A cubed, which means that, let's say A times is by 4 randomly. What is the rate times by? Yes, Kushi, there are 0 order reactions and we'll be talking about those in a second. 4 to the power of 3. Yeah, 4 to the power of 3 or 64. Wicked. Ooh, that should be a 4. Yeah. So just because Kushi sort of mentioned it, even though we'll be covering it a bit later, I'll put in a note that you can get 0 order reactions or reactants that are 0 order. And that essentially means that they don't affect the rate. That you can like put in as much of them or as little as them as you like, and it won't affect the rate of reaction. And that's a really specific case. And we'll be looking at that in more detail in just a bit. But well done, everyone. Yes, 64. Okay, so what we're going to do is look at units because chemistry likes to confuse us. And the units change for the constant K depending on what the order of the reaction is. So we either have to work out what they are or we have to memorize what they are. And I'll start you off with the first order, and then you guys are going to help me out with the second order. So we know at the moment that rate is equal to K times the concentration of A. There might be more reactants, but we're keeping it simple for this because it gets a little bit complicated. So rate equals K times A. And if we want to work out K, then we rearrange by moving that A to the side of the rate, and we get K equals rate over the concentration of A. So if we have K equals rate over the concentration of A, to work out the units, all we do is substitute in the units for these things. So we don't know the units for K because that's what we're trying to work out, but we do know that the rate is always moles per dm cubed per second. And we do know that concentration, as we sort of said earlier on, is moles per dm cubed. Can anyone tell me what's going to cancel out in this equation? Does anyone have any ideas? In this fraction, what two things are going to cancel? Yeah. Yes, Zane. Yeah. Yep. You're all right. So because you've got moles per dm squared on the top, cubed on the top, and a moles per dm cubed on the bottom, they cancel. And in this case, in the case of a first order reaction, the units for K are seconds to the power of -1 or 1 over seconds, depending on how you write it. Yeah, exactly, Zane. Wicked. Yes. So this is for first order. So I'm going to do the same. I'm going to write out what second order looks like. So in second order, we'll have K equals rate over A squared. If you remember, we end up squaring things. So if that's the case, we're going to have K equals moles per dm cubed per second again for rate. And then we're going to have moles per dm cubed for A, but it's going to be squared. So does somebody want to tell me how that would simplify? How would it cancel? Not quite, Maisie. Yeah. Some of us are getting it. So it should be, we should have one of these cancel. So one of the powers cancel out and the top one disappears as well. So you get seconds to the power of -1 over moles per dm cubed. Yeah, exactly. So because you guys have seen first order and second order, does somebody want to just take a stab at what third order is going to look like? I will go through it, but does somebody want to have a guess? Or an educated guess? Should I help you guys out a bit? So, oopsie. Oh, yeah, we're getting it. Yes, so because there will be a cubed in there because it's third order, we're going to end up only cancelling one of the bottom ones, which means that we'll end up with seconds to the power of -1 moles per dm cubed squared, which you can either cancel out, sort of expand to moles squared, which I shall write for you, moles squared dm to the -6. Yeah, you guys are all brilliant. So we've had some, what I said is right, just on the other way. Okay. Yeah. Isn't moles the power of 1 dm cubed S1 the same as S1 over to the power of -1? Sorry, Emma, it's hard to read what you're putting in the comments because there's no subscripts or superscripts. So let me just give me a sec. Moles to the power of -1 dm cubed S to the power of, yes. Yeah, it's the same. You can write it either way. It's just a bit clearer this way. But yes, it's going to be a bit tricky to see you guys' answer today because you can't, obviously you can't do the squared signs in YouTube, but we will make do. Okay. Right, so the next thing that we need to talk about is, this is where zero order pops up. So to calculate overall order, essentially we're going to have to recap indice laws from your maths GCSE or from last year, or if you're doing maths A-level, it should be pretty easy. So the first thing we want to remember is if you don't see a power, what does that mean? If there's no power, what number is technically there? Yeah, thank you, Fatima. Thank you, Zain. It means that there's a 1 there. So we have to keep that in mind when we're working out our overall order. If you don't see anything, it's a 1. So what happens, because of course we've got this concentration times by this. That's what 2 brackets next to each other mean. So when we're timesing indices, how do they actually combine? Does anyone remember? Do we times the indices as well? Or is there something else that we do? Add. Yeah, Shell, yeah, Logan, you add them. Yes, Zane. Wicked, you add them. So in this case, we're going to be adding this power and this power. So it's 2 plus 1, which I'm not going to insult you by asking you to do, because I know you can do that. 2 plus 1 is 3. So if you're asked for the overall order of reaction, the only real stumbling block will be you forgetting your indice laws, because you just add up the orders. And keep in mind that that should be a 1 there. Oh, it zoomed in. How interesting. Okay, so again, if you have a 0 order reaction, can I tell you the best book for chemistry self-study? So it depends on your exam board. So the exam board's textbook will be really specific for the exam board that you have. There's also the CPG books, which are generally quite decent. But of course, we have SnapRevise and we have videos as well, and a bunch of study guides. So I can't not recommend those because I think they're really good, even though they're not a book. Yes, hello world. It's CGP. Did I say CGP or CPG? One of those letters in some kind of arrangement, but I should get back to it. So when the concentration of reactant has no effect, the rate is 0 order, as we sort of mentioned earlier. So another indice law that you guys need to remember is that when something is to the power of 0, what does that actually mean? Anyone? Yeah. Yes. Yeah, lovely. So it means that it's 1. So you can kind of see how that affects the rate equation, right? Because we're saying that rate is equal to the concentration of these reactants is proportional to them. And we've also said that 0 order means that they're not proportional. So if we had B being to the power of 0 because it was a 0 order reactant, we would end up with rate just being equal to A times 1. So it's not actually included in the rate equation. But there'll be another sort of example of that later. So this is the first section done. Hopefully it was not too bad for you, but let's see how you guys are doing. And Roberta, I will answer your question in just a second. Can I get some emojis or some numbers to tell me how you're feeling about this topic? Do I need to go back and explain something again? Or can we go on and do the exam questions? Got a 1.5, got a 1. Smiley faces. Ooh, a very smiley face. Full smiley face. Oh, that's a confused face. Hello world. Do you want to tell me what sort of, and Tommy? Anyone? What does half mean? Oh, it means 1/2. Okay. If the exam questions, please, says Zane. Is there a specific part that is confusing? Because it's useful for me to know what exactly is going wrong, and then we can go back and look. Anybody want to say something that's specifically confusing? You have 10 seconds to do so, because we've had a few faces. Logan's good. Zane wants exam questions. All right, I'm going to move on to the exam questions. Just sort of, Zara's confused with everything. And Charlotte wants to know if there's any definitions that we need to know. So far, Charlotte, you need to know the rate equation. So you need to know that rate is equal to K times the concentration of the reactants to the power of whatever the order is. What is rate determining step? Hello world. Rate determining step is something we're covering next Thursday. So I'm not going to be covering that now. But briefly, it is the step of reaction that determines the rate, but that's quite a detailed topic. Let me go back up to Roberta. Is there a way to remember practicals or answer practical questions for exams? So we're actually going to be looking at a practical question in a second, Roberta. That's why I kind of was leaving your question till after. Zara doesn't take chemistry? Then you are a dedicated student, and also chemistry is awesome. So if you're staying for that, then, you know, I totally agree with you. Cool. All right, I'm going to move on. So if anybody was like super confused about everything, like literally everything, then there's a questions bit at the end, and I can go back and explain it all over again if you need to, not for like a whole hour, but sort of like you can tell me specifically which bits and bobs, but I'm going to carry on for now. So here we have an experimental question. So with experimental questions, the most important thing is A, to read the question, and B, to make sure you understand any graphs or tables properly. Don't glance at them, because especially with rate, there's lots of different but very similar diagrams. So we're going to be really careful about what this is. And I cannot get my pen out. There we go. Yes, I can have pen. Right. So a student investigates the reaction between iodine and propanone in the presence of aqueous hydrochloric acid, and the results of the investigation are shown below. So here we have concentration of iodine on the bottom in moles per dm squared. Please, please, please always check the units, because they do like to trick you with those sometimes. And then we also have initial rate on this side. So this is the initial rate of reaction against the actual concentration of iodine. We also have these rate experiments. So we've been given the concentration, and we've been given the rate of reaction for the reaction, which would make sense, depending on the rate. So the question is, determine the orders with respect to iodine, propanone, and hydrochloric acid, the rate equation, and the rate constant for the reaction. Explain all your reasoning. Okay, you're dead. Somebody's dead. Is it because chemistry or because something's funny? I hope it's because something is funny, not because you're actually dead. Why are you trying to be a Peaky Blinders wannabe? Oh no, let's not be mean. Please no meanness in the chat. I2 is 0, surely. Oh, beautiful, Maisie. Iodine is 0 order. Wicked. All right. So you guys have jumped straight ahead while I'm looking at your comments. Good. It is good that you are joking, Zara. But yes, let's keep it nice, please. So we have this here, and we can see that the rate does not change when iodine is increased or decreased in concentration, which must mean that iodine is 0 order. So we have to explain our reasoning. So we need to say something like no change of rate when the concentration of iodine changes. So remember, you either have to do your square brackets, or you have to say the concentration of. Either is fine, but make sure you do one. So it's 0 order. So we've got our first point. So now, there's been some drama in the chat. Please, no more drama. Only chemistry. That would be really nice. So we've got what iodine is. So the next important thing to do is look at the table, because the graph was only really giving us any information about iodine. So if we have a look at, let's try and look at this one first, propanone. So we've got experiment 1 is at 1.5 times 10 to the 3 concentration, and experiment 2 and 3 are at 3 times 10 to the minus 3 concentration. So then we look at the rate, and we want to see how the rate has changed when we've doubled this. So we're only looking at experiment 1 and 2 for propanone, right? Because that's the only time it changed. And hydrochloric acid, as you can see, helpfully did not change at that point. So we don't need to think about that. So when that doubles, what happens to the rate? Does the rate double? Does it double squared? Does it times 2 cubed? How does it change? Anyone? Yeah, exactly. Thank you, Fatima. Thank you, Maisie. So when propanone doubles in concentration, the rate also doubles because 4.2 is double 2.1. So we have to write that really specifically. So we say when propanone, and because I'm lazy, I'm writing the chemical symbol instead of writing propanone. Oops. Times is by 2. The rate times is by 2. So it's first order. Okay, last one. We're going to look at our hydrochloric acid, which means that we need to look at experiments 2 and 3 because that's when its concentration changed. So when we went from 2 to 5, what do we need to times 2 by to get to 5? Somebody want to shove that in their calculator? Or does somebody just know? What do we times 2 by to get 5? Yeah, we're timesing it by 2.5. So we need to figure out if this times by 2.5, do we times, is this also times by 2.5? Is it times by 2.5 squared? What is it times by? Yeah, I mean, I'm seeing, yes, thank you, Fatima. Yeah, it times is by 2.5 again, which means that it's what? First order, second order, third order, 0 order? Anyone? First, yeah, thank you, Vivian. Thank you, Logan. Thank you, Fatima. Oh, no, Logan, not quite. It's not second order. No, yeah, it's first order because when you times them by the same thing, when you times a concentration by one thing, the rate also times is by that thing. So we're doing when HCl times is by 2.5, the rate also times is by 2.5, so it's first order. Is this basics of year 13? Yes, Tommy, this is basics of year 13. This is basics of rate. So this would be a 3-mark question. I think it got chopped off the end, Zane, but this would be 3 marks. So you would get 1 mark for each. But keep in mind that you really have to say why. So it says explain your reasoning. And that means that you have to say when that doubles, the other thing doubles. Otherwise, you don't get your marks. So just sort of try to be as over-explanatory as is humanly possible. So I'm happy with that. I think it's time to move on. So the next question, the next section, will I be going through? Not this, Sidika, I won't be going through rate determining step in this session. That's the next one because rate is a really big topic. So rate determining step is in the next one. But this is all the things you need to know before you do rate determining step. But yes, so that will be next Thursday at 6:30. Concentration time graphs. So that's the next part of rate. So if you've noticed so far that the sort of most important part of our rate equation that we can actually measure is the concentration, right? And to be able to measure concentration, we have to do it over time. And that's called continuous monitoring. And you I put it in red because it's one of those keywords that need to be in exam questions if you're talking about how you measure concentration. So you need to say continuous monitoring. So what we're really doing with this is trying to figure out what kind of methods you can use to measure concentration as you go. So like over a 10-minute period, how do you keep measuring the concentration of the reaction without the reactants, without like stopping the reaction altogether. So we've got some sort of headings here to give you a few clues. The first heading has 2 answers. So if a reaction produces a gas as the product, how can we sort of continuously measure that? Does anyone have any ideas? So we just be going, yes, Sadika. So I'm just going to really quickly skip back to the first part. So the objectives tell you what we're covering. So thank you, Fatima. Sorry, I'll get back to it. But Sadika, so we're going to be doing rate equation, rate constant, orders of reaction, concentration time graphs, half-life, and then using concentration time graphs to find rate constant. That's what we're doing. And I'm going back to blah. Yes, so lovely. Fatima, yes, we can use a gas syringe or a gas cylinder to measure the volume. Yeah, change of volume. Yes, thank you, Vivian. Perfect. Vivian, why did you retract your message? You totally had said some good stuff in there. But yes, and then we can also, somebody say mass. Yeah, so change in mass. So essentially we can measure sort of the weight loss. Because if you're letting the gas escape rather than collect it, obviously your sort of whatever your reaction chamber is, be it like a conical flask or a beaker, that's going to get lighter. So you can measure that as well. So what about acid reactions? How could we possibly measure the rate if we have sort of a reaction that's either using up an acid or creating an acid? Any ideas? You will have done this experiment, even if, yeah, so we can measure change in pH by, yes, you guys have put it all together in one. Thank you, Emma. Thank you, Fatima. So we're going to be measuring a change in pH using titrations usually. So you would be adding a base and then checking the concentration at regular intervals that you need to neutralize. Litmus paper is not actually accurate enough, Zane, to measure things like that. Sort of litmus paper can tell you the gist of whether something is sort of something is acidic or basic, but it's not time exact enough to be able to tell you, oh, at this moment it changed. So what we need is to titrate with some kind of base. So a good sort of strong base example is always sodium hydroxide, and then at regular intervals, we can measure how much base is required to neutralize, which will tell you how much acid there is. And then, of course, you could use a pH meter as well. Oh dear, so we have more drama in the comments. Oh no. Yes, so if you're removed, you should probably try to stay removed, because, you know, if you were removed, it was because you did something wrong, and we want this to be a nice space for people to come and learn and just not, you know, be insulted. I like to learn without insults as well. Yes, okay, so last one is color change reactions. How can we measure the progress of a color change reaction? Anyone, any ideas? No, yes, maybe. So precipitation, that's an interesting one. So precipitation reactions, how would you, Zane, expand on that? What would you do with that? Yes, Vivian, colorimeter was what I was going for, but Zane has said something interesting. So just do you want to see cross through the flask? Yes. Cross. You keep cross. Cross. I see. Yeah. Okay. So if you're sort of basically The cross under the conical. The cross under the conical? So do you mean that like if you have a precipitation reaction, once you can't see the cross anymore, the reaction is done? Is that what you mean? Yes, that's what you mean. So that might not be exact enough. You'd be better off if you have, so Fatima, as I said at the beginning, we're not going to be covering the iodine clock example specifically. We're going to be covering its overarching sort of topic because it's in half-lives. Iodine clock is sort of a really specific version of that, but we'll be doing something like it. But yes, so back to the disappearing of the cross. So what we really want to do with a precipitation reaction or a color change reaction is be able to measure it really exactly. So if we just do it by eye, that's not very exact. We want to use something like colorimetry, which can tell us how much light can get through with a really specific figure. So looking at it is not so great, but we can use colorimetry. So I'm going to put that in. And remember, guys, taking notes is better than not taking notes. Even if they're like really like minimal notes, just having to write something down makes your brain engage with it more than if you don't write something down. You're welcome, Fatima. So if it's a color change specifically, you're going to be measuring the complementary color. Can somebody tell me what a complementary color is? Yes, getting on to that. Does anyone know what do I mean by complementary color? Light absorbing, like yellow and purple. Opposite on the color wheel. Yes, exactly. So essentially, when you have a color, let's say you've got a color change that is going from clear to green. So a light is going to be shining through your little burette, and I'm going to like draw it. So if our light is shining through here and there's like a bunch of green stuff in there, it's not the green that's being absorbed. It's the complementary color of the green. So if the complementary color of green is red, then all of the red light in this tube is being absorbed by the sample, and that's why you see green. So if you see something blue, its complementary color is being absorbed. So if you remember your color wheels from art, the one on the opposite side is the thing that's being absorbed, and the thing that you see is the opposite. Is this OCR-A? This is OCR, EdXL, and AQA. Sadiqa. So yes, so if you measure the complementary color absorbance, then it can tell you how much of the color change is happening. Is that all making sense? I suppose we'll do, I actually just want to see, did that explanation make sense of the colorimetry? Can I see some emoji feedback? Never knew that. Yes. I always find color chemistry really interesting. It was one of the sort of first things I thought were really fascinating. We got a wink. I'm going to assume that means that you got it. Yeah, we seem happy. Okay, let's go. We're going to look at the actual graphs themselves and what they can tell us about what's going on. So a concentration time graph can tell us whether something is zero order, first order, or second order. So what are we looking at here? If we're thinking about this, we're calling it sort of reactant X. So here we have a sort of situation for first order, because can someone tell me what happens while the concentration of what is happening to the concentration of the reactant? Anyone? In the first order reaction, over time, what's happening? It's decreasing, yeah. And it's decreasing for all of them. Yeah, it reduces. Does anyone know what shape this is? This kind of curve is decreasing linearly. So it's not for the first order. For the zero order, yes, it is linear. It's concave almost. It is concave, but that's not the word I'm going for. It's a mathsy word, if that helps. Not sure? Exponentially. Wicked. Yes, Logan. So this, specifically for first order, this is called exponential decay. And it's just a very specific shape. And as somebody said, the zero order is linear and the second order is still curved, but it's more of an extreme curve than first order. Ooh, I can't write extreme apparently. Can't use technology, how? Okay, more of an extreme curve. So in your exam, you won't ever be asked sort of to judge first order or second order without the other one there. So it's never going to just show you a random curve and be like, what is the order of the reaction? It will show you something like this, but without zero order, first order, and second order written, and you'll have to identify by comparing them. So don't worry about the fact that the difference between the curves for first and second order is not that obvious. Yes, so you can see the most sort of important thing to mention about this is that you can see for zero order that the concentration of X does not affect the rate. How do we know that from this diagram? And this is quite a difficult question, so it's okay if you do not know the answer. But how can we tell just by looking at this, apart from memorizing it, that the concentration does not affect the rate? Any ideas? It's something about the fact that it's linear. It's directly proportional. Yeah, kind of. Getting there. Yes, Fatima. Yeah, it's because the gradient is constant. So I don't know if you guys have ever sort of like made the connection between gradient and rate, but gradient always means change in, right? The gradient is telling us how the concentration changes over time. And the way that concentration changes over time is the rate. And the rate is constant. So the concentration of the reactant does not affect the rate at all. Hi, will you explain when the tables get confusing and sometimes decrease? It's not easy to work out. Billy Chow, I don't know what you mean by that. Could you possibly rephrase that question? And while you rephrase it, I will write down that X does not affect the gradient and hence doesn't affect rate. Like when in the tables they all change simultaneously. So they shouldn't change simultaneously and check. Do you mean, sorry, I'm just gonna pause, gonna go back. Do you mean like in this question where the rate change, you've got the concentration changing and the rate changing? As in that graph we were looking at before, it was simple to work out because B didn't affect the reaction. Is this the page you mean, Billy? Yes, that question. And sometimes decrease. What do you mean sometimes decrease? I don't know what you mean by that. Because essentially with these questions, what if the numbers weren't easy to work out? I'm afraid that's just going to be a practice thing, Billy. Like you're going to have to do loads and loads of them. I will say that there will never be a table where you've got all overlaps. And by that, I mean like here, you've got propanone doubling from here to here, and the hydrochloric acid stays the same. So it won't, Maisie. There will always be at least one part of the table where they don't change. So zero order is when there's a constant rate, even when the concentration is changing. Is that what a zero order graph is showing? Yes, Fatima. That is exactly right. Zero order is when the rate does not change when the concentration changes. Does that, Billy and Maisie, does that answer your question? So what I'm saying is that there won't ever be a table where there isn't some time where one of the reactants stays the same concentration and the other one changes. It should always be like that. Is that okay? Do you still have questions? We got sort of, yeah, that's fine. Okay, Maisie, you got about 5 seconds before I move on. If that's still confusing. All right, if it is confusing at the end, it's just that it gets confusing. It does. So the way I like to do it is by sort of I like to go step by step. So I like to look at the propanone and be like, okay, I'm just going to look for where does the propanone change. I double check that the other reactants aren't changing. And then I just stop looking at the hydrochloric acid and I only look at the propanone. So I think it's sort of maybe about staying focused on each reactant as you go, rather than trying to look at the table as a whole. But there are more reaction questions, so perhaps you'll get to have time to practice that. But I'm going to move on. And if it's still confusing at the end, do let me know and I can explain some more. So yes, so the only note I'm going to make for second order and first order is that as the concentration of X goes down, the rate decreases. And we can tell that by the changing gradient of the curve. No, I don't mind, Billy. At the end, we will talk about it. So second order, it's not actually exponential decay because the gradient of the curve isn't quite right for that. But it's sort of an extreme version, but we don't have like a mathematical name that we want to name that really. But all you really need to know is that as the concentration of the reactant goes down, the rate decreases. Okay. All right. So we're going to be thinking about half-life. I'm going to sip my tea because mouth gets very dry talking this much. You have to at least half like the sound of your own voice to be a teacher. Otherwise it gets quite tiring hearing it all the time. Okay. So half-life and rate order. As we could see for this slide, it's really difficult to tell the difference between first order and second order by looking at it. They're very similar. And there is a way to determine whether it is first order for sure, and that is half-life. So what we do is that we look at, so we've got concentration and we're using C here, but let's say we've like got a random reactant. Let's say this is hydrochloric acid. When hydrochloric acid has halved in concentration, we go across the graph and then we go down the graph and we measure that time. So let's say that was 30 seconds. That's important for us to measure. And then once we've done that, we halve again. So let's say that was like 60 moles per dm cubed, which is massively concentrated, but never mind. And that was 30. Then we would halve again and go down to 15. And we would go across from 15 again. And then we'd go down and we'd measure the time. And if the time is the same, it's a first order reaction. So that means that a constant half-life means that the reaction is first order with respect to that specific reactant. We don't learn how to tell if something's definitely second order. We just learn, I'm sorry, I've just looked at my own writing and it's really bad. If my handwriting is illegible, please tell me. Because obviously it's my handwriting, so I know what it says, but I don't know if you guys know what it says. So do let me know. So can someone tell me what the half-life concentration would be if this were a 3 mole per dm cubed solution in the first place? What would the half concentration be? Anyone? 1.5. Yes, Maisie. When the graph goes straight across, that was a slightly different graph. That's why I said it's so important to check the time and concentration. The graph from the question was an initial rate graph, and the graph that we just looked at was concentration time. That's why one of them was straight and one of them was a diagonal. But yes, so whoopsie. So that's 1.5 moles per dm cubed would be the half-life, and we would go across and check for 30 seconds. So I'm about to ask you guys how you are feeling. How is all of this feeling so far? Are there any slides you want me to go back to? Please mention specific slides if they exist, because if the super confused face only helps if I know what you're super confused about. So Logan is happy. I'm glad. Ooh, you're welcome, Maisie. There's a big silence here. Does that mean lots of you are writing which slides you'd like me to go back to, or that you're confused about whether you're confused? Only 3 responses so far. You can also say that you don't know what you're confused about. Could I go through Half-Life again? Yes, I can. Yes, I can. So I'm going to scribble everything out. All right. So Half-Life is literally just a way to figure out if something is first order, because from here we can see that first order and second order look really similar. So if we want to be able to tell if the curve is actually exponential, if it's actually a first order reaction, then we can work this out from half-life. So what half-life means is when the concentration halves, how long did that take? So I'm going to actually make a note. How long does it take for it's not a word, for the concentration, let's just call it X, to halve? So I'm assigning random numbers. So if the concentration was 100, then 50 would be the half concentration. You go across on the graph and you go down to the time. Yes, I will, guys, go back to that exam question. So we're at, let's say that this was 30 seconds, or even let's say that it was 1 minute. So we would know that the first half-life is 1 minute. So that doesn't tell us anything yet. We need to get a second half-life. So we go from 50 being the concentration and we halve it again to 25, and we go across and we go down again. And if that is another minute, if the half-life stays the same after the second and after the third and after the fourth halving of the concentration, then that means that we have a first order reaction. So if the half-life stays constant, the reaction is first order. Zane asks, so does half-life only apply to first order, not second? Yes, exactly. This is how you determine whether it's first order, from the fact that curves look the same by eye. You don't learn how to figure out second order reactions from a concentration time graph in A level. You don't need to know that. You only need, so if the half-life doubles, no, you don't learn anything to do with half-life at A level for second order. You only learn first order. So we don't do that in that. We are going to come across how you figure out something second order or not. But for now, I'm going to go back to, I cannot remember who asked me to go back over that. Let me scroll up again. Zane, does that make sense now? Because I want to go back to that exam question. Is that all good? I'm getting no response. So yes, it does. Now it definitely makes sense. I was lying when I put a smiley face. Don't lie. I can help if you tell me that it's confusing, but I can't help if I don't know. And the cool thing about being on the internet is that you don't have like people around you that you grew up with that you feel might judge you if you ask a question, because nobody here on this comment section knows who you are, unless you got friends on there, in which case, sorry. There's nothing that can be done about that. But yes, let me delete these annotations, and then we will go back through this question. So the important thing that we sort of were getting confused about in the comments is, why is this a straight line? Why do we have a straight line here? And then when we were looking at here, it's diagonal. And this is because if you notice, this is a concentration time graph. And this one is an initial rate concentration graph. So you must look at what kind of graph it is. Hassan, you are quite late. You are an hour and 5 minutes late to class, but this is the internet. So it doesn't matter in like the we'll check you out way. It just matters in the you can't ask questions for the earlier parts when they were happening kind of way. So this graph, I feel like we all got that meant that it was zero order. So I'm just going to really quickly go through strategizing for this question, or this part of the question. So I really want you to ignore hydrochloric acid for a sec and just think about propanone. So propanone is this one. It's this one here. And there's only experiments 1 and 2 is the only place that propanone changes its concentration. And if we quickly glance back at hydrochloric acid, we can see that it does not change its concentration at that point. So we just have experiment 1 and 2, and we can see very clearly that it doubles, right? That it doubles in concentration. And we can also see very clearly that the rate doubles. And that means that we have a direct proportionality. We have the concentration of this thing is directly proportional to the rate. And that means that it's first order. And we have the same thing for HCl. So again, we're now going to ignore propanone. We're only going to think about hydrochloric acid. Oh, Roberta, I'm so sorry. I know those feels. Working is tricky to balance with your studies. I worked throughout my studies, and it was very stressful. So you have all my sympathies, and you can watch this video later. And then if you do sign up to sort of our ultimate package, you can also just like ask me random questions. Billy Chow, hi, please look at my values. I don't understand how to do it. Concentration D, initial rate. All right, Billy, if these are from like a book or from an exam, what I need you to do for me is to screenshot it if it's on the computer, or take a picture of it with your phone and then send the picture in, because that is really difficult to decipher. And we'll do that at the end instead of this one right now. So try to get that for me because it's really difficult to read that. If you already have SnapRevise subscription, will this be included when it comes out? I'm going to let can you like drag it into this? Sorry, Billy, can you drag it into this box? Does it pop up? If not, then send it to georgia@snaprevise.co.uk and I will pick that up. Cool. My colleague has answered that question about web classes. But yes, so my name is spelled like this, Billy, if you can't drag it in there. And you can send me over that question and I'll have a look at the end. Okay. So do you guys have the value already? I don't know what you mean by the value, Roberta. But yes, so what I'm going to do is really quickly finish off. Can I have the full email? That is the full email. It's right at the top. Right. So I'm going to give you guys, Billy, I'm going to give you till the sort of end of this question to see that email address. So we already covered propanone, and we saw that when it doubled, the rate doubled. So now we're looking at HCl. It doesn't change between experiments 1 and 2. It only changes between experiments 2 and 3. And as we said before, we know that it times is by 2.5 because 2 times 2.5 is 5. And so what we want to do is check if this times is by 2.5 as well. So if you shove in 4.2 times 10 to the minus 9 in your calculator and times it by 2.5, you can see that it does equal this, which means that it's also first order. So if you change the concentration and the rate changes by the same amount, then that means it's first order. And I'm going to move on from this question because we've been on it for quite a while, and I will come back at the end if we need to. But I want to move on to the exam question for this whole section. So propanone reacts with iodine. Again, we've got a lot of propanone happening in this, as shown in the equation below. So propanone is this one, and iodine is, of course, this one. And the rate equation goes like this. Rate is equal to the concentration of propanone times the proton concentration. So the most appropriate technique to investigate the rate of this reaction will be what? And Zane has already answered and is, I'm not going to say whether you're right or not because I'm going to let other people have a go. First, is it titrating samples of the reaction mixture with acid? Is it measuring the optical activity? Is it measuring the volume of gas given off? Is it colorimetry? Yeah. 2 answers is enough. Yes, exactly. So it's A, because the only clue you get is that it's an acidic solution and that there's H plus in there. So we know that acid is involved. And now we also know that acid is in the rate equation, the acid product. So titration with acid has got to be the way to do it. So yes, thank you, Zane and Fatima, for getting that. And we're also going to look at some rate graphs. So which of the following graphs shows that a reaction is first order with respect to reactant X? And I want you to be really, really careful at looking at what the actual graph is. So these two are concentration time graphs, and these two are rate time graphs. So I'm going to let you guys sort of stare at that for a bit. Any ideas? Anyone else want to come up with? So DC thinks C, Vivian thinks C, Shell, Connie, yeah, it's C. So I think, Zane, that you were right in seeing the sort of exponential curve, but it's C because as the concentration goes down, time is moving forward. And of course, that's true because it's a reactant. So you want the reactant to be going down over time. Yes, cool. People have gone and see. All right, so we can finally do our last section, which is determining the rate constant in first order reactions. So this is, we've sort of been looking at how you tell something is first order, but we haven't really looked at how you sort of derive the rate constant. And if we remember, we have rate is equal to K times the reactant. And the only reactant we know about in this is this one, right? It doesn't say anything else. We have no other information. So we've got rate equals K times the concentration of iodine. So if we want to know K, how do we rearrange this? How can we rearrange this equation so that K is the subject? Anybody? Yeah, thank you, Maisie. Thank you, Vivian. Wicked. So we've got K is equal to rate over the concentration of iodine. So the way that we sort of work this out, so if we know that K is equal to the rate over the concentration of iodine, what we do is we need to know what we put in to this equation, right? Like which rate, which concentration of iodine, because we've got like a bunch of concentrations of iodine. We've got like, goes all the way from 3 down to 0. So it's a little bit confusing to use just that. And the way that we choose what sort of concentration to take and what rate to take is we draw a tangent, and you can draw the tangent anywhere on the curve. And a tangent literally just means, like, you know, when you have a circle, anything that goes off the edge and touches only one point is a tangent. So you can pick any point on the curve and draw a tangent to it. And in this case, this tangent, let's say, is roughly sort of ends up at 1.25. So we've got 1.25 there. And does somebody want to give me like, what is this time roughly? Anybody? Just a really rough figure. Yeah, like 3,000 or something near there. So we know that we want the rate and we know that we want the concentration. Does anyone remember, how does rate relate to things on a graph? What sort of value on a graph is going to tell us the rate rather than just the time? The gradient. Thank you, Logan. So if you guys remember that gradient, I mean, you should have done this like year 9, year 7, earlier than that, maybe even. So gradient is rise over run. So the way that you're going to do it is K is going to be equal to the gradient. The gradient of the tangent you just drew over 1.5. Change in conc over time. Yes, Flashman. Yeah, change in concentration over time at a specific point is going to be the gradient of the tangent. So I'm not going to make you work out the gradient of the tangent unless you really want to, but because it's really simple maths, I don't really want to waste time on it. But it's rise over run. So the rise has got to be 1.25 and the run is 3,000. So I'm gonna leave it at that. But that's how you would estimate K from your concentration time graph. So it's easier to determine the rate constant from half-life instead of doing that, because that requires you to draw on your graph. Drawing a tangent on your graph isn't going to be very accurate unless you're doing it on the computer. So it's easier to do it if you have sort of an exponential of your first order reaction. And if you remember this guy here, T subscript a half is half-life. So we're looking at half-life again. Does somebody want to tell me, like, where should I be? How do I get half-life from my graph? Where do I start? Start from 5. Yeah. What do I do with the 5? There, you were right. Yep. So we started from 5, and to get the half-life, Logan, you're correct, it's 2.5. So you half it and you get to your 2.5 and you go across on your graph and we get to like here maybe. And then we go down. I'm going to sort of try and make that slightly less dodgy. Cool. So then we go down. Hi, Billy. Thank you. I will have a look at that at the end. So I'm going to call that time like 45 seconds-ish. That looks reasonable. So we're going to use this equation, and you do have to remember this equation, I'm afraid. You don't get it in your exam. So because if you remember, we know that this is an exponential graph if it's first order. And the opposite of the exponent is the natural logarithm. So that's what this is, that's ln. You don't have to half again. That's if you're trying to work out if it is first order. We've assumed that this is first order already. So we just need one half-life. We just need the first half-life, and that's 45. So in this case, we literally just shove in our calculator, k is equal to ln2 divided by this, which is 45 seconds. And that is a much faster way of figuring out the rate constant than having to work out a tangent, then do rise over run, then divide by that. This is definitely faster, right? Does somebody want to shove that in their calculator? ln2 divided by 45? If somebody's got a calculator with them. If you've got an iPhone and you turn it to the side, your calculator turns into a scientific calculator. So you should also have ln on your phone. If you're an iPhone user, anybody? Or are you going to force me to do my own calculations? It would be a terrible, terrible act. Oh, look at you, beautiful people, lovely people. Saving me calculator use. Okay, so yes, you are right, 0.015. Yeah, I mean 154, but we're going to sort of round to 3 decimal places. But yes, both Logan, Maisie, Zane, you're all correct, and I appreciate it. Does anybody remember, if we go all the way back to the beginning of this this thing, Webclass? Sorry, my brain is starting to just melt, apparently. Does anyone remember the units for a first order rate constant? And I will be so proud if you remember what it is. How long until the end? This is the last sort of information slide. It's not quite, Maisie. Yes, Logan. It's reciprocal seconds. Yeah, Fatima, for first order, it's reciprocal seconds. Yeah, Billy, this is the last information slide. We've got an exam question. Then I'm going to chat to you guys about some SnapRevise things, and then we got questions. Oh, wait, that's 2. What's 2? Yes, Maze. Oh, right. You mean the second order. Yeah, what you put was the second order one, but the other way around. So, you guys have done so well. All right. How's that feeling? Does that make sense? So we've got the tangent method, which is long, and then we've got ln2 over half-life, which is less long. Did all of that make sense? I'm gonna need some emojis or some slides if you didn't get it. Yes, hello world is feeling very cool, and Hassan and Logan, we're all good. Happy, we're feeling happy. Yeah, okay. Nobody's saying, please help me. I am confused and lost. So I'm gonna go ahead and do some exam questions. Fatima, I cannot tell if that is a grimace face or a happy face. Billy, the 2, I think we can still go on to the exam question because that might help things. This is a long one. The A2 ones are quite long for chemistry. I might, because this is sort of the first year 13 class, it sort of might tell us whether we need to chop them up a little bit. It's a happy face. Okay, cool. It's a happy face. Got it. We haven't started Half-Life stuff yet. We did do Half-Life. We definitely did Half-Life. Half-Life is physics. So Half-Life just literally means half, like when you have like any amount of substance, if there's half of it and it's degrading over time, that's half-life. So that might be applied to radioactive decay, which is more physicsy, but also some chemistry. Or in this, half-life is, yes, wait, no at school. I'm confused. This is a long one. No at school. I'm confused. We should have started with thermodynamics, but teacher says don't do it according to the chat search. Just give the answer to the next exam question. I did. I'm confused. All right, I'm going to move on to the exam question because the comments are currently puzzling to me. Okay. Oh, I did. Yeah, I forgot what the next exam question was. Oh, well. Maybe I didn't give it in enough detail. Okay, so we're moving on to this question. Another lovely experimental question, so get some good practice. And please remember that the most important thing is to actually check what graph you are looking at. So in an aqueous solution, benzene diazonium chloride, C6H5N2Cl, decomposes above 10 degrees. So we've got this lovely equation, and then the student investigates the rate of the reaction using an excess of water. An excess of water means that there's sort of like so much water that we don't include it in the rate equation because it's basically constant. The student takes a measurement at intervals during the reaction and then plots his experimental results to give the graph shown below. The student uses half-life to suggest the order of the reaction with respect to benzene diazonium chloride, what is meant by the half-life. So I just asked that question, and I'm seeing in the comments that you're saying that you haven't done it yet at school. I'm afraid the difficulty with doing lots of exam boards and doing cross-school stuff is that firstly, the exam boards do a lot of year 13 in different orders. So it's all the same thing, but they just have it in a different order. And secondly, some schools do it in a different order. So some schools will be like, I don't like that this is first in the textbook. I'm going to start in the middle and go backwards. So like it really, I'm afraid that it just can't be helped. It's people do things differently. And this is the one that sort of was most popularly the first thing. So that's why it's first. But yes, I'm going to, I mean, like as Fatima said, I gave away the answer to what is meant by the half-life of a reaction, but you guys should know that already because we've been talking about it. So do people want to write me a comment? What is meant by half-life of reaction? Hassan says the half-life of reaction T to a half is the amount of time needed for a reactant concentration to decrease by half compared to the initial. Oh, what a beautiful definition. That is, you know, you're kind of nerdy when you think a definition of half-life is beautiful. But yes, that is absolutely true. Next time, for the next question, I'm going to kind of ask you guys to try not to write anything in for like 20 seconds to give people time to answer themselves. But yes, so we have time of concentration. Oh, time of concentration, time for concentration. So the time for concentration to fall to half the original value. So that's a nice simple one. If you can just memorize that, you have a mark. And it kind of says it in the word, half-life. What is the half of its life? So the next bit is confirm the order of reaction with respect to benzene diazonium chloride. Show you're working on the graph. So obviously this is going to be a little bit difficult for you guys to do unless you've printed out the little thingy. I'm so sorry. My brain is obviously just having a bit of a tantrum about using words at, what is it, 8 o'clock. But what's the first thing I want to do? What am I going to be looking at on my graph? Someone help me out. If I want to confirm the order of reaction of this, what do I need to do? Yes, Logan. Yeah, thank you. We need to figure out what the first half-life is. And this drawing is going to be so dodgy because it's really hard to get straight lines. So like, please bear with me. But can someone tell me, so if we've got sort of like this point here, let's call it 5.8. Can someone tell me where am I going to be drawing? Yeah, Logan, you're totally right. We're comparing it to the second. So Shell is calling that 6. It's not quite 6, and that might just be because you can't see it close enough. But that is more like 5.8. Yeah, 2.9, something like that. Yeah. So I'm going to really try and draw a line that's not dodgy, but it's going to be dodgy. All right, straight enough. Straight enough. And then we're going to come down in a roughly straight line. Oh, okay. So let's call that what? Let's call it 56 seconds. Okay, so if we did that at 2.9, what is my second? What value do I need to go to on concentration this time around? Anyone? Yeah, something like that, 1.45. I'm saying something like that because there's no way I'm going to be able to get to exactly 1.45 on this screen, but bear with my very wiggly line. But in your exam, obviously you're going to use a ruler. Definitely use a ruler. So if we look at that number, so we know we're looking for it to either be the same or not the same. So it's either going to be 56 plus 56, roughly, because obviously my graph is rubbish. So if it's 56 plus 56, that should be roughly like 112. And I think we can probably say that that is kind of like 112 seconds, right? It's close enough. So if those two half-lives are the same, so if that T half is the same as that T half, what kind of reaction do we have? What order of reaction is that? It's first order. Yeah, thank you, Logan. So it is a first order reaction because our half-life is constant. So it's 2 marks. So you'll get 1 mark for show you're working on the graph. And the second mark will be saying what it is. So we're going to put in that the half-life is constant at 56 seconds. So the reaction order is 1 with respect. Ooh, wide. That's an interesting word, isn't it? It's not a word. With respect to C6H5 N2Cl. And please, please, please put what the reaction is, what the order of the reaction is respect with. Jesus, I'm so sorry. My words just aren't happening. Please put which reactant the order of the reaction is with respect to. Ha, ha, I said my words. Because if you don't, it doesn't count, because you could be talking about the order of the whole reaction, or you could be talking about the order of a different reactant. And I know that this question specifies it, but I would still write it down just to be sure. People, we have made it. We've made it to you should now be able to. So you should be able to understand the rate equation, the rate constant, and orders of reaction. You want to know what those things are and how to use them. You want to be able to look at concentration time graphs and analyze them for the order of the reaction and for half-life. And you want to be able to use those graphs to find rate constants of first order reactions only. So that is what you should be able to do by now. When I say you should be able to, what I mean by that is once you revise the topic 2 or 3 times, you should be able to by heart. Of course, the first time you learn something, or even the second time you learn something, it's not going to be in there totally. Your brain doesn't really do that. It needs repeats so that it can tell itself that that information was important versus that cat video that you watched last week. So be okay. Okay, cue the Dora Explorer song. I haven't watched Dora Explorer for many years and I don't remember what it is. Billy, we're getting to that. I have to do all of the housekeeping and show you guys SnapRevise before. What revision guide do you remember for chemistry? Do I recommend for chemistry? KF, could I recommend anything but the SnapRevise revision guide? No, I could not. I really couldn't, because that would be madness. Okay, so on that topic, we have our 2.0 thing coming up, which we're really excited about. So I'm gonna I know we've been here for like a really long time, so I'm going to do a really quick whiz through of what that is. So essentially we have the basic package that will have teaching videos, an exam walkthrough, and revision guides. Okay, so that is what I was talking about. And you can sign up for sort of like the most basic-y stuff now, and then once it gets to October the 16th, you'll be automatically upgraded to the 2.0 basic package. And then if you want to, you can upgrade to Pro or Ultimate. And Ultimate is the one where you have me doing all the web classes. Even though some will be free, most of them won't be. They'll be on the Ultimate. But yes, if you can't afford it, don't worry, I'm still here for you. You'll also get me as sort of like a drop-in tutor. So like you can like send me messages and I will answer them about things that you're confused about, which is super helpful. So yes, so if you want to sign up for that, we have a discount code coming up in just a few minutes. Yes, this was a long one, wasn't it? So yes, we have more web classes that are free coming up, and what I'm going to do is really quickly show you our beautiful website. Oh no, I gave you the code, but you only saw it for a second, so you can what's it called, just sort of pretend that you didn't see that, because I cannot find the this is so hard. Technology is so hard. Okay, so here we have all of the web classes that are coming up. And we have reminders, so you can set reminders for them. So if you want to come to the next year 13 one, which is going to be rate and the Arrhenius equation, which will also include rate determining step, that's next week, Thursday, and you can set a reminder so that YouTube will tell you when it's happening. I'm going to go back to the thingy now, and hopefully will not show you other random things from my computer. Yes. I make me laugh too, mainly because like I cannot use this computer apparently, and it's just I just messing it up. I'm so sorry, guys. Hopefully my chemistry is better than my PowerPoint using skills. So here is your code. You have lasted the whole thing, which is really great. And you have a code and you can get our course for £17.97. Oh, how exciting. Yes, so do that. And then once the October 16th comes out, you can upgrade and it'll be cheaper than if you were going to sort of like wait till October 16th and then just buy the package outright. Billy, I'm so sorry. I'm almost there. We're so close. We are so close. Yes, I can, because we're at the any questions slide. You've been so patient. I'm just going to open my emails in a different... Oh, no, I can't open my emails in a different thing. Okay. I'm not going to open my emails in a different thing. I am going to go to my emails. And I assume that you can just see me right now, because I have to find the question. I'm so sorry, Billy. I'm not seeing the question. Oh, I am seeing it. It's all good. Yeah, yep. Okay, yeah, we can only see you. Thank you, Fatima. All right. Okay. So what I'm going to do is chuck this in. Just bear with me, lovely people, and I will... This is so just for everybody else, this question is sort of another one like the one earlier, where you've got like a bunch of initial concentrations and then the rate changes. So I'm going to go through this question for you guys, but I just want to chuck it on the presentation so that you can, so I can annotate it. So just give me a second. Dum, dum. Oh, My computer hates me. So ha. Ta-da. All right. Thank you guys for bearing with me because I believe I have the question for you now. Okay. Dum, dum, dum. Right. I should be able to share this with you. Right. Okay. So you should be able to see the question now. Yes, you are like you're proper fans of A-level chemistry, which is fabulous. I'm really hoping that right now you can see the question that's just popped up. So I'm gonna. Can you just confirm for me, because I can see the web class, but my computer's being really slow, so there's a lag. Can you guys tell me if you can see the question? Yes, you can see it. Wicked. Okay. So it says, this question involves the use of kinetic data to calculate the order of reaction and also value for the rate constant. The data in this table was obtained in a series of experiments on the rate of reaction between compounds E and F at constant temperature. Work out the order of reaction with respect to E. Okay. So we're going to look at E, and we're only going to look at E where it's changing and the F is not changing. So that means that we can only look at E when it changes between experiment 1 and 2. We can't look at 3 because F has changed. So E, what does E times by? Can you guys tell me what E times is by to between experiment 1 and 2? 3, yeah. We times, so 0.15 times by 3 is 0.45. So what we need to do is figure out if the rate of reaction has also times by 3. What do we think? So what we really need to be putting into our calculators is 3.78 times 10 to the 3 divided by 0.42 times 10 to the 3. Someone chuck that in their calculator? 9. Okay, cool. So this is times by 9. So we need to be able to say that rate is proportional to the concentration of E, and it's going to be, yeah, so it's second order. So we know it's squared because 9 is 3 squared, right? So that is the answer to that bit. So we've got, so it's got space for working. So it doesn't ask for your working, so we can just say that it's second order. Right, so the next part of the question, I believe, was to work out F, but I'm going to have a look at that because I couldn't manage to fit it on the screen. So I'm just going to double check that that's what it wants, is to work out F. Yes, it does. Deduce the order of reaction with respect to F. Cool. So we've got E changing from this to this, and this isn't a very nice question because essentially we've got E changing, we've got E doubling as well. So this is going to take a little bit longer. So we know that E is second order already because we worked that out, right? So I'm going to like scribble out all of this working because we're going to need space for working out F. So because E is second order, the first thing we want to do is figure out how much the rate of reaction would have changed if the only thing that changed was E. So what would happen to, so essentially what we should be doing, we know that E is now doubled. We know that it's times by 2, which means that if E was the only thing to have changed, we would times by 2 squared because it's second order. So if somebody could chuck in their calculator 3.78 times 10 to the minus 3 times 2 squared. 15.12. So that doesn't make sense for so 4 times 4. Can we measure the velocity? So it can't be 15.12 because it's going to be times, it should be times 10 to the minus 3. That's better. Thank you, Maisie. So 0.015, or we can put that as 1.512 times 10 to the minus 2. So it can be either. So this is what it would have been if we had only doubled this. So what we're going to do is be looking at the difference between this number here and this number. So we've halved this. Yeah, thank you, Abdullah, as well. So we've halved the concentration of F, and we know that it's not 0 order, right? Because if it was 0 order, this would be the answer. It would be 1.512. Well done, Fatima. Yeah, my brain is also fried. It's a little bit fried, people. So this should be 1.512 times 10 to the minus 2. Can anybody put in their calculator what you would times this by or divide this by to get 7.56 times 10 to the minus 3? That would be super helpful. And then we should have a bit of an answer. What is 1.512 times 10 to the minus 2 divided by 7.56 times 10 to the... Yeah, it's a change of 2. You're dividing by 2 to get from there to there. And this is divided by 2. So if it's directly proportional, then what order of reaction do we have? Anybody? First. Yeah, it's first order. So with respect to F, we have a first order reaction. I don't have a little box to write that in. But yes. Billy, is that question making sense now? Or everybody else? Anybody? Does that question make sense? So if you have one where both sort of values, the concentration values are changing, then you need to sort of use your knowledge of how the first one changes. Yeah. Okay. Yay. Okay. Right. That means that does anybody else have any other questions? If not, then we're done, but I'm happy to answer some more questions if you have them. Anybody? Abdullah gets it. Oh, I'm so glad. It's nice. It's nice when your teaching works. Okay, nobody's saying they have other questions. I'm going to give it another 20 seconds and then I'm going to say goodbye to you and go eat some snacks because I'm super hungry. Oh, the free account. Would I be able to do the other example? What other example, Billy? Yes, the free account hasn't been revealed yet. Oh, colleague, do you have the free account announcement? Have you disappeared? No one entered. No one entered. Oh, that's so sad. No one posted. Does that, Fatima, did you think that that you had done it? What's the I did, but I got it yesterday. Did you tag us? Sorry, I'm looking at the comments and trying to look at the question at the same time. The duration of that constant temperature. Yes, I can, but you will have to bear with me again because it means I have to download that question and shove it on there. Just 1 second. Right, Billy, my internet is having a bit of a hissy fit and it doesn't seem to want to download the question. So what I'm going to do is possibly write some notes for this question and get my colleague to post it with the rest of the web class. And then you guys can all see it later, but I'm having a little bit of a malfunction and I can't get the question to download properly on my computer. And as it's the sort of same methodology, I think it would be worth me, instead of us sort of hanging around and me trying to figure out how to make my computer function, I'm going to try and get my colleague to post it with the video when it uploads. But I really would like to help with it. So I'll make sure that that gets to you guys at some point. But it's been so lovely. I'm going to turn this thing back to me because yes, so what I'm going to do is say goodbye. It's been really, really lovely teaching you all. Thank you for staying right to the end. I'm really hoping that somebody gets to win. Oh, Fatima, I'm so sorry. Yay, I'm glad I helped you understand. It's really gratifying to be able to actually, you know, help students rather than just staring at you like they have no idea what you're talking about. Yeah, Fatima, if you can screenshot your phone with the tag in, and then send the picture of it to the email, then we should be able to figure something out. But yes, I will see you guys next Thursday, hopefully. Yes, staring at books is not the best way to learn, especially if you're trying to absorb the information by osmosis rather than reading it or doing questions. So I'm gonna head, guys. I hope you have a lovely evening. See you next week.